Lesson 36 is the last lesson of this unit, de Broglie wavelengths, and it's one of the more bizarre lessons you will ever have in physics. And before you go through this lesson, you need to go to YouTube and you need to Google Dr. Quantum double slit experiment, and you need to watch one of these videos. This one, proof of mind over matter. Watch out when it's got something stupid at the end, but watch this video and then come back. And if you are not wanting to bang your head against the wall after watching this video, then you didn't pay attention, because it's got some crazy stuff at the end about quantum mechanics, quantum events, and should throw you for a loop a little. Okay, so based on the last lesson, we discovered in the last lesson that something without mass, light, X-rays, have momentum. So along comes de Broglie and says, well, okay, if waves, if EMR, something with no mass, can have momentum, does it not stand to reason that particles can have wavelengths? And so he suggested exactly that, and he combined two formulas. He combined the two formulas that we went over in our last lesson in the Compton effect, the momentum of a particle, the momentum of an X-ray, or EMR, and he combined them, because if P equals this, P equals that, then that must equal that. And he got this new formula. This is a derived formula. It's not on your formula sheet. This allows you to calculate the wavelength of something that has mass. Okay, and it's a very easy formula to use. And here's an example. Determine the de Broglie wavelength of a 0.2 kilogram ball moving at 15 meters per second. The formula was the wavelength equals h over mv. So it's very simply plugging in the numbers. M 0.2 V 15 meters per second. So you're throwing a 0.2 kilogram ball at 15 meters per second. What's its wavelength? Well, you turn out to get this answer. 2.2 times 10 to the negative 34 meters, which is extremely small. That's it's so small, there's no way you have any hope of measuring a wavelength that small. So an object like a ball, a big object, has an extremely small wavelength. But and that was very impractical, because there's no way you can measure that. If you look at the formula, you can see that something with a decent amount of mass is obviously is inversely proportional to wavelength. So it's something with a big mass is going to have a very small wavelength. Something with a smaller mass, a much, much, much smaller mass, has a wavelength, is going to have an increased wavelength that we may be able to measure. And that's what it discusses in your notes, the hard part, finding experimental data to support the theory. And then it goes back to talk about Young's double slit experiments, which if you watch the Dr. Quantum video, you will be familiarized with again. And it talks about wavelengths of electrons. So electron has a very small mass, so maybe that's something that we can measure the wavelength of an electron. And in this example, number 2, it says determine the wavelength of an electron accelerated by a 100 volt potential difference. First, we have to calculate the velocity of the electron using the formulas used in the electricity unit. So the electron has kinetic energy, right? And we're trying to calculate the velocity of the wave of the electron, that it's being accelerated through a potential difference. And the formula that we learned from that unit is that E equals QV. So it's accelerated through this potential difference, giving it a kinetic energy, and therefore we can say that 1/2 mv squared must equals Q big V, right? Velocity, voltage, not the same thing. And you can use this formula, you can manipulate it and solve for V. V equals square root of 2q big V over m. Right, put in all those numbers. Remember, we're talking about an electron here. So it's going to be 2 times the charge of an electron times the voltage divided by the mass of an electron. And that will give you the velocity of 5.93 times 10 to the 6th meters per second. And then in step 1, in step 2, you can calculate the wavelength because now we know the velocity and we know the mass using the formula that we derived earlier. Oops. Okay. Don't need brackets there. And we end up getting a wavelength of 1.23 times 10 to the negative 10, which is, again, it's an extremely small wavelength, but it's something that's within the realm of us measuring. And if you read further in your notes, it talks about Davison and Germer. They did an experiment here. They shot electrons at a crystal sample of nickel in a vacuum tube, and they observed a diffraction pattern. So we're going back to that Dr. Quantum video where we're shooting particles through 2 slits, and they produce a diffraction pattern. It's absolutely mind-boggling. And so they proved this. They proved that this actually happens and that particles actually have wave properties. So, and if you remember the double slit experiment with electrons, so first you did the double experiment with light. You shone light through the 2 slits. It produced an interference pattern. The light diffracted, produced an interference pattern on the other side. Then you do the same thing with particles, and you wouldn't expect in a billion years for particles to produce a diffraction, an interference pattern, but they did. And so particles can have wave properties. And then the bizarre thing was that then when you try to watch the experiment happening, the wave function breaks down and all of a sudden they're behaving like particles again. And that's the weirdness of the quantum world. There's a saying that if you think you understand the quantum world, you don't. Bye for now. We'll see you in the next unit.